So this talk will be in two parts. The first part, I will give the setup from learner point of view, the categorical local Langlands conjecture. And the next part, I will try to put other packets in this context. Okay, so this will be the outline of the talk. So first of all, I give some notational setup. We fix a prime number P, a rational prime number, and let F to be a p-adic field. This capital gamma is the absolute Galois group of F. Small k is the residue field of F, and we know it's a field of characteristic P. For the sheaves that we want to construct, the scalars will be defined over an L-lectic field. So we fix another prime L, which is different from P. If you want to make things convenient, you may take L to be large enough. Sometimes I will take a field L, which is an L-lectic field containing square root of Q. And the scalars will be denoted by this lambda. Usually this capital lambda will be the QL bar. Sometimes it will be the complex field. That is the classical case. Okay, when we talk about classical local Langlands correspondence. Or even sometimes I just take an L-lectic field L or its ring of integers. Even is a residue field. So that is in Fargues-Scholze setup. They allow their scalar field or even scalar ring to be non-algebraically closed. So the further the scalar field being non-algebraically closed, the statements will be more complicated to prove. But in any case, here I would just usually assume lambda to be QL bar. There's one hidden thing in the background. So that is the category of perfectoid spaces over K. Okay, so I won't go into detail, but you may just imagine everything is defined over this category. We also have for each perfectoid space, this XS is the relative Fargues-Fontaine curve. Okay, so maybe I will talk about a little bit about this curve. But for now on, all these are in the background. So I will just state the statement about the conjecture, the categorical local Langlands conjecture. So we fix a reductive group G over F, and the conjecture directly given by Fargues-Scholze. It says that there's an equivalence of stable infinite categories, okay, whatever that means. The two categories on the left-hand side, this is the derived category of these compact, let's say sheaves on bungee. And on the right-hand side, we have the derived category of, okay, a lot of dressings here. These are bounded, quasi-compact, coherent sheaves on part G, which has nilpotent singular support. Okay, so later on, I will explain these objects, bungee and part G. Okay, but you can roughly imagine this left-hand side is the side of representations, and the right-hand side is the parameter side in the classical situation. So this equivalence has some properties. The actions of, okay, this perf part G is the subcategory of the right-hand side that contains the the so-called perfect complexes. This is like all those complexes with I think it's about the complexes that cohomologically is bounded and projective, I think, yeah. So as a subcategory, of course, it has a canonical action on the right-hand side, but on the left-hand side, the action is given by so-called spectral action by Higgs operators. So I will mention a little bit later. So this is one property. Another property is that the structure sheaf on the PAR-G side corresponds to the Whittaker sheaf on the Bun-G side. So this Whittaker sheaf is like the Whittaker model. You say, I should say this G, you can take, you can assume it to be an extended pure inner form, so of a quasi-split group. So for the quasi-split form, then you can fix Borel, and you take the unipotent radical, and you fix a non-degenerate character of that. This is that is the Decker F here. I'm sorry. Yes. Can you say again what PAR-G is? PAR-G is the moduli stack of the parameters of G. So I will explain it later. So G bundles on the partial vector. The G bundle, that is the Bun-G, right? Sorry, no, Bun-G. What is it? What is it? Bun-G is the moduli stack of G bundles or over XS. What? The XS, the relative Fargues-Fontaine curve. Over the Fargues-Fontaine curve. Yeah. And
yeah. Did I understand you to say that the left-hand side is more like the automorphic representation and the right-hand side is more like the parameters?
Yes. 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 The representation side and the Galois side. Yeah. And then yeah. Can you explain what PAR-G is? Later on, I will give a description. I just give the statement straight away, but yeah, as I said, later I will describe these objects. Hmm? One of these be the dual group. This PAR-G is defined using the dual group. Yeah. Any other question, comments? Very welcome. Okay, I should say this is the first time I give this talk, so any comments is welcome. No, then I continue. There's another version of the conjecture, so which is related to L packets. So let's say this G is quasi-split, and I assume a parameter var phi to be elliptic. So this parameter, okay, let me see. First of all, you can think about it as a morphism from the Weydilin group, which is the Wey group cross SL2 to the L group. And to say it is elliptic, I mean this is a discrete parameter. That means it's centralizer of this parameter is finite mod center. And I also want it to be trivial on the SL2 part. So roughly thinking, you can just imagine this is like a morphism from Wey group to the L group, or a one cocycle from the Wey group to the dual group of G. So, and it's elliptic. You said we should think of it that way. Is it really going to be something about RG that we don't know yet? Okay, if you want, maybe I just tell you PAR-G is just this moduli stack of the one cocycle from the Wey group to the dual group, quotient the adjoint action of the dual group. This is PAR-G. I think some people, they denote it by log cis of G hat. This is, I should say this conjecture, the first statement, this is also proved in a series of papers by Gaisguri in the function field case. I mean, or you can think about this is the equal characteristic case. So they have a series of papers given by Gaisguri's group. Here, our setting is based on the Fargues-Fontaine curve because this is their strategy to prove this conjecture in the p-adic group case. Does it make sense? Okay, as I said, just ask any question if you don't understand. I try to answer, but I guess there are many experts here, so if I don't know the answer, I just pass the question to some of you. Okay, so let me continue from here. So quasi-split group, Varphy is elliptic. Then this is another conjecture that is given by Fargues. I think in his 2016 note. So there exists a unique generic representation, pi phi, whose L parameter is var phi. And there's an equivalence of categories between the perfect complexes of the classifying stack of SV. So this side, more or less, you can just think about it as the representation category. I mean the derived category of that. And on the right-hand side, this is the derived category of the Lissé shift on Bungie. But we focus on those. We focus on the component that is coming from this C var phi. This C var phi is the connected component in par G that is containing this var phi. And this subcategory is the one that corresponds to the par G side, those sheaves that are supported on this C var phi. And the category is given by this functor. So this V going to V acting on this par phi, this pi phi, pi var phi. This is a generic representation here. So this action is the spectral action that I will mention later. Let's see, what is the, such that each row, if you take V to be a representation of this S var phi, irreducible, then it corresponds to this pi phi row, which is the conjectural representation under the local Langlands correspondence of G. So, which one? SV, yeah. This is the centralized group of var phi in the G hat. Yes, pi 0.
I'm sorry about the first bullet. You are assuming that you have the Langlands Langlands classification.
I think so. Here I think I assume the classical local Langlands.
Local Langlands.
The sort of the bijection of parameter with the L packet. Yeah.
And even not tempered.
Non-temporal. Here I just assume it is elliptic. Yeah, that is Fargues' statement. This is another version of the conjecture. So this is given by Fargues in his 2016 paper. Is it? Okay, maybe it's not a good strategy to. I'm just stating the conjecture that those experts gave in their notes. Yeah, it's a good question. Why I say those are theorem? Because I think some people are working on specific examples of these statements. So I think some people are working on GLN. Even GLN has some technical part that I would say I don't really understand, but at least I know that it's still in progress. And for classical group, I think there are some very new papers from some students. I forgot their names, but there are some people working on particular example of these. So in some instances, this is a theorem, but I would say in general, this is still a conjecture. C5 is the connected component of this phi. Okay, you think about phi as just a point in par G. Yeah, so this is the connected component. This is the category corresponding to those sheaves supported on that component. Okay, maybe, as I said, maybe not a good strategy to directly show you these complicated statements, but I will explain all these in the slides, in the following slides. So what is par G? Okay, so par G, I think Gay-Scully's paper, they use this log-cis of G hat. I'm not sure why, but I prefer to use this par G. So it's in Kashtan's and Varshevsky's paper. So par G is the moduli stack of the space of one cocycles from the Ray group to the dual group of G modulo the adjoint action.
I'm sorry.
Yes?
I should understand this very well. These one cocycles, what do they have to do with homomorphisms to the L group?
I think, are they the same thing? To the L group, yes.
Think of it as an L homomorphism, or you could forget to WL factor.
Yes, thank you. Does it convince you? No?
Well, I have no idea what the storm of G hat.
Oh, okay, okay. This is the classifying space of G hat. So star is just means a point. Okay, so this is the natural projection that you sort of collapse the whole par G into a point. This is just a natural map that I will use later.
And so par G is the cocycloid space. Is that the, what is it?
Par G is the moduli stack of parameters. Okay. Yes. Okay. I really appreciate some of you help me answer these technical questions.
But when you look at the local systems, G hat is defined over what basis?
What basis? I'm not sure. Yeah, it's a good question, but this is just a notation used by Gay-Scully. So you ask Gay-Scully maybe.
When you're saying what does he have to find over, are you asking about the date frame?
Yes, I mean, he's asking whether you.
Yeah, I mean, jihad is not defined over what.
Yeah, you could even do this over the adjoint one over K.
But finally, if you are going to get the one-one correspondence, you have to know which you take on which side.
Sure, and I mean for the classical local Langlands correspondence, you work over something like that.
On 12 bar, which is C.
Yeah.
Okay.
Thanks, David. Yeah. So, should I continue? Okay. So let's say if phi is elliptic, then the connected component containing phi is this C var phi that I mentioned. But this is just the classifying space of the centralizer group of var phi. So to understand the spectral action of the category of perfect complexes to the derived category on Bungie. Here, Kastan-Rashevsky gave a nice reduction to reduce the statement sort of back to the usual representation theoretic statement that we see in the classical local Langlands. So here we embed this kinetic component to G, and as I said, it can project to the classifying space of the dual group. Then this is just the usual functoriality for the of these functor. So you have the map from the perfect complexes of classifying space of G hat, which, as I said, this is equivalent to the bounded derived category of the finite dimensional representations of G hat to the corresponding derived category, but for the centralizer group as var phi. Then the action of a representation of G hat, okay, you put it as a perfect complex in the classifying space of G hat. The action on this piece, the C var phi piece of the derived category of Bungie, you can reduce it to looking at the action of this V restrict to this as I think this is S var phi or C var phi. I think this is C var phi here. Okay. C var phi is here. Connected component. Bar, what bar? Va, sorry for the English. Va phi. Maybe I just say phi, okay, phi. Oh, sorry about that. Okay, va phi. I think the latex, this symbol is va phi, right? Yeah, sorry, phi. S phi, okay. Does it make sense?
So the first time I took the lead groups course as a grad student at MIT.
Yes.
Austin, but Chinese grad student came up to me afterwards and asked what these letters alpha and beta are that Austin talked about.
Oh. Okay, maybe he should have learned some Greek. Okay, so.
I think if you just go on,
Yeah.
will probably make more sense.
Yeah. This is a good idea. So Bungie. So Bungie is the stack of group points over the perfectoid space over K. So if you put a perfectoid space, then you get the set of G bundles over the Fargues-Scholze curve. So there's a stratification of Bungie all these strata, they are parameterized by this BG. This is the so-called Chord-Width set of isocrystals. So roughly speaking, these isocrystals means you have conjugacy classes of elements in G, but the scalars are in the maximal and ramified extension. Okay, roughly speaking. But what we need to know is some simple properties about this BG, which will be useful later on. So Bun-G, you look at the closed points of Bun-G. This is exactly this Chord-Width set. This BG is ordered by the so-called Newton, or I think some people call it a Harder-Narasimhan polygon. This is a map from the BG to the set of this Galois invariant dominant co-characters of G. So here I fix a maximal torus T in G. So we have this dominant co-character. This set has natural order if you also fix a Borel. So this order is brought to BG. There's okay, each stratum, okay, on BG is the classifying space of the automorphism of G bundle, okay? I think any G bundle, okay, corresponding to this B. This automorphism group, in fact, if you take the pi 0, then you will get this GB of F. So then this gives a natural map from the classifying space of odd EB to the GB of F. So, and then we say G bundle E is semi-stable if it has no proper non-zero subbundles with slope. So this is just the Newton polygon. Remember, this is ordered, so we can talk about this subbundle that is greater than nu of E. And being semi-stable, it means there's no proper non-zero subbundles with slope greater than this Newton polygon of E. And a G isocrystal is basic if this bundle, corresponding bundle, is semi-stable. So we will mostly look at basic G isocrystals. Some facts: there's a bijection between the set of all isocrystals to the character of the Galois invariant of the center of G hat. This GB group, I think when it is basic, this GB is exactly the automorphism group of any G bundle corresponding to B. So this group is an extended pure inner form of G, okay? So if B is basic. So then you see here, I'm trying to reduce the Bun-G to the representations of reductive groups in this way. So there's a statement saying that if you look at those, let's say, sheaves supported on the B stratum of Bun-G, this category is equivalent to the representation category of the pure inner form GB of F. So in this way, I relate this kind of a Bun-G thing to representation theory of p-adic reductive group. Is it, does it make sense? Okay. Anything wrong? Any comment from expert? Extended pure inner form, I think maybe I need some help, but okay, my understanding is just coming from basic isocrystal. But very first definition of extended pure inner form, I forgot what it, the definition. Sorry, maybe some expert here can help. Okay, anyway, just think about this GB is coming from a basic isocrystal. So here I have explained some simple properties or simple definition about power G and bund G. Now I will go to talk about the spectral action, but I need some basic setup for that. This is about Grassmannian and the Higgs stack. So we define this LG, which is the loop group. Okay, if you put a perfectoid space, this is the group with scalars in this. This field is the, let me see how to explain this width ring over OF with let me see. Is the width ring generated by S, but you also invert this uniformizer in OF, so making it a field. Roughly speaking, you can imagine this is like the maximal unramified extension of F. Okay. If you find it is technical, usually I just think about it as this maximal unramified extension. There's a subgroup of that, the L plus G. This is the jet group. You put the this width ring. This is again more or less like the ring of integers of this maximal unramified extension. You put in the G as scalars. So here I sort of suppressed a little on the notation. In fact, both groups can be upgraded to some scalars that is that contains the scalars that is in the field defined by a divisor. You can choose a certain divisor in this Fargues-Fontaine curve. So this is like those people working in the athletic field, this global situation. When what I mean is that this, okay, maybe I talk about a little bit about this Fargues-Fontaine curve, because the idea of Fargues-Scholze is to sort of mimic the global argument in given by Laurent Lafort. Okay, so but here we have this local situation, but yet they come up with this Fargues-Fontaine curve that so that some statements in the global situation can be sort of mimic some of the statements in the global case to the local case, and they try to use the technique from there. And this divisor is like the situation when you know this those guys, when they do modular forms, they have this GA mod GQ, but they also have G of a certain sort of this subgroup with the integral subgroup with some conductor. So this divisor plays the role of that conductor. Okay, if you have a larger conductor, you try to understand more the geometry of the automorphic space. So in any way, I just don't write down the divisor version of these loop group and jack group, but just bear in mind they can be upgraded to some more complicated situation. And that will be, let's see. Okay, anyway, I will talk about it later, okay, when I try to use a little bit about the upgraded version using the divisor. Let me continue. So we have this local Grassmannian. This is the moduli stack. Sorry, the quotient stack of LG by L plus G. This Grassmannian has a description using G bundles and an isomorphism between this bundle to the trivialization over the punctured disk. So if you forget about that isomorphism, you have this functor to Bungie from the Grassmannian. You can do one more quotient, and this is the Higgs stack. Okay, it again has some G bundle description. But as a geometric object, you take this set of Higgs G. So this is the Satake category of G. Is the category, the full subcategory of those so-called universally locally acyclic flat perverse objects in the eta shifts of Higgs G, the derived category of that. So again, too many technical constructions, but just think about we have some sheaves on this Higgs G. But as a Satake category, actually, let me say this is exactly the object that connects the two sides of the categorical local Langlands conjecture. So how does it work? This Satake category is a symmetric monoidal category. So there's a product that you can take in this category using Lustig's convolution. And there's also equipped with hypercohomology functor from the Satake category to this is just a category of vector spaces over the scalar field lambda. But this can be identified with the Satake category of the maximal torus of G. So this sort of giving you the idea about the usual Satake correspondence, right? From the representation of G to characters of T. As a symmetric monoidal category, sorry, I should say this setup this symmetric monoidal structure with this hypercohomology forms a natural Tannakian category structure on this Satake category. And we can look at the automorphism group of this hypercohomology functor. This is isomorphic to the Langlands dual group of G hat. So from something in the Bungie side, we construct something on the dual group side using this Satake category. And more precisely, this is a theorem given by Merkovich, Vailonen, and Gaisgori. So there's a equivalence between these symmetric monoidal categories. On the left-hand side, this is the representations of finite dimensional representations of I pieces of LG. This I is just an index set. Remember, I said I can upgrade my setup with into the situation when I have the Fargues-Scholze curve deleting a divisor. So then this index set will show up. Okay, so this is just I pieces of the L group of G. There's also a version, the I version of this Satake category of G. So just think about it as sort of some upgrade of the usual Satake category. But if you want, you just think about this. I is a singleton, so it's just a simple equivalence from the representation of LG to the Satake. To give a rough sense of how these objects correspond, you can look at the IC shifts on the Higgs stack. Okay, remember this Higgs stack is related to this bungee. On bungee, we have an order given by these polygon, and those polygons are parameterized by dominant co-characters. I fix one co-character and I sort of pull this stratum to the Higgs stack. Okay, so this is the one, and I take closure of that. And the IC shift on this the closure of the Higgs stack corresponds to this representation on the of LG. So what you have is this V mu, the highest wave module, parameterized by that dominant co-character mu. This is a representation of G hat with the trivial action of the wave group of the fixed field of mu, and then you induce it to the full L group. So this is the R mu. Okay, so this is the representation here that corresponds to the IC shift on the Satake side. Does it make sense? Yes?
Sort of.
Okay. Yeah.
This is an old theorem. Yes.
This is a theorem. Yes. Yes.
Did they phrase it like this, or is it?
I think I think the symbol should be correct. Except I still have to make more sense about this side, this upgraded version of Satake. But as I said, you just think about it as just one piece of this category. But to define the spectral action, you need to really use the upgraded version to use the full power. Okay, any other question? So then now I can talk about the spectral action. This Satake transform, which is this statement. So it gives rise to this sequence of functors. So representation of the L group of G to the, this is the full derived category of the Higgs stack. It also goes to another similar category. This one, this regular H hat is the global Higgs stack defined in this way. So you have two pieces of G bundles, and this beta is an isomorphism that relates these two on the Fargues-Scholze curve, deleting a given divisor. So there's a natural map. Okay, if you go back to the definition of the local Higgs stack, it goes to the sorry, it's another way, global to local. Okay, and this, you take the derived category of sheaves on these two. So let's say representation of the L group goes to a sheaf denoted by SV. Then this SV will be used to define the Higgs operator. So here is global Higgs project to bungee by taking the first piece. You can also take the second piece to bungee, but okay, this is a technical part which I still yet to understand, but roughly speaking, you also remember this divisor. And you do this kind of pull back, push forward, but sort of like doing a Fourier transform, okay, with this character SV, okay, to a given shift on bungee. So if you project back to bungee, then this operation gives you an anamorphism on this derived category of bungee. So all these are coming from this given representation V on the representation side. And remember, this one is related to the perfect complex of par G. Yeah, so so in this way, we have this operator. This is the Higgs operator, and it gives the spectral action of the which I mentioned before on this sheath on bungee. Here is black triangle. Sorry, black square is something about what they call solid sheath. Is in the context of condensed mathematics of Peter Scholze. So I think I won't talk about it. Okay. So yes. We have no time. Well, okay. This is still the first part. Okay. Maybe okay. Let me go straight away to this statement. Okay, so this is the last conjecture in the first part. So if we have a discrete parameter, there's a sheaf on bungee. Let me just call it a Fargues sheaf, such that, okay, there's a Higgs eigensheaf property and L packet property. But here it gives you a construction of this Fargues sheaf. You take the point that corresponds to this phi, this phi, and you push forward the trivial sheaf on the point. So this gives you sort of a skyscraper sheaf on par G. This is a coherent sheaf. Okay, sorry, this is a quasi-coherent sheaf. Not coherent as at the beginning, but you can identify it with the sort of the in category of perfect sheaves on par G. Then this F var phi is conjectured to be given by this E phi acting on this Whittaker sheaf. So this is Fargues conjecture. From this construction, I will state method to sort of give a conjectural construction of other sheaves, other packets. So let me go to the second part. Sorry for the timer. Let me go through it. Okay, let me show you everything and I talk about it quickly. So here I change a little bit on the notation. Phi previously is used for denoting parameter. Now it is denoted as lambda, okay? And we call it an infinitesimal parameter. Phi is now used to denote parameter from the V group cross SL2 to the L group, which is called Langlands parameter. And we define an other parameter to be morphism from so-called the, let me just say this is a V group cross two pieces of SL2 to the LG, such that it satisfies some conditions. These restrictions are just like a shorthand notation, okay? If you really go to the definition, you'll see some matrix with eigenvalues q to the half power and its inverse, but I just don't want to write down those matrices, and I use these shorthand notation. Okay, you can go back to Arthur's paper to look at the construction. Anyway, we have defined Arthur parameter, and Arthur's results state so Arthur's paper stated that there's a finite multiset of representations on the unitary dual of G. This is so this packet is constructed by endoscopic transfer. So that means those representations, they satisfy some character relation, okay, given by endoscopy theory. And there's a map from the Arthur packet to the representation of, this is a centralizer group of the Arthur parameter. And it contains the L packet of the Langlands parameter corresponding, given by this Arthur parameter. This set is really a set if G is quasi-split. So this is Maclin's result. Okay, so how to construct the A packet? So there's a way given by is inspired by Adams, Babbage, Vaughan. Later on, Clifton and his group, they give the p-adic version. So we fix infinitesimal character, infinitesimal parameter, denote H lambda to be the centralizer group. And sorry, say again. This is p-adic group. This is on the dual side. So lambda now is infinitesimal parameter. It's just V group to the L group. Yeah. And V lambda is consisting of those tangent vectors, okay, in the this centralizer group of the image of the inertia group of F by this lambda, okay, and I take the Q eigenspace of this lambda of this Frobenius. This is V lambda. We can define the opposite variety by changing the eigenvalue to Q inverse. You take the quotient step and you look at the closed points. This is in bijection with those Langlands parameters, whose infinitesimal parameter is this fixed lambda. Okay, so here you see this setup is giving a parametrization of the Langlands parameter. So we define the following geometric objects. We have cotangent bundle, just V lambda cross the opposite V lambda. And we look at inside the conormal bundle associated to a certain C. This C is an orbit. Here, you think about this is just an object in V lambda mod H lambda. So it corresponds to a Langlands parameter. I mean this C. Okay, so this conormal bundle is those tangent and cotangent pair, where this X is in C and X with this second piece C has a Lie bracket 0. So here, implicitly, I identify these two pieces by this symmetric form. Okay, so it's killing form. You can also look at the regular piece of this conormal bundle. So these orbits, they form a stratification, and you just get rid of those which is on the boundary. Okay, so you get the regular piece corresponding to this C. So here I use the definition of this vanishing cycle functor given by Clifton's paper, Clifton and his group. So this is the I guess I won't give the actual construction, but I just say this is a functor from the bounded derived category of the stack V lambda mod H lambda with support on C to the derived category of the regular part of the conormal bundle over this H lambda, but you put a disk over the scalar field lambda. So in their paper, they show that this functor maps perverse shifts on one side to another. And this shift is represented by a shift we denote it by AC on this V lambda mod H lambda stack. This is the other shift in their paper. Okay. I think if you put it in Fargues-Scholze setup, yes. But this is on the dual side. Maybe no. Actually, what is the use of this? This, yeah, this is the trait. This is what they call the trait. You can think this is the spec of like this. I mean this is ring, right?
I mean, it's just spec of this.
In their setup, yes. I think you just replace this C by this QL bar. You can still go through all the construction. I think formal spectrum, yes. This is crucial, is it? This disk product. So here we use the whole disk or the puncture disk. Either one. Okay. With these sheaves. Okay. So I will just give you the conjecture. So here, associated to this other sheaves, we put it on the power G side. So my conjecture is that this could be a perfect complex or not. I'm not sure. But if it is non-perfect, we can still extract the perfect part and I would think this perfect authorship acting on the Whittaker shift, giving the author packet. So I think even though this conjecture may not be completely correct, but this spectral actor shift by the this so-called author shift is still worth to study. So sorry about all these technicalities, but yeah, this is the end of my talk. So as let me just say thank you, and I just at the end want to show I don't know what to show to express the legacy of Jim Arthur, but I think all these websites summarize everything, and it's really a great honor to be Jim's student. So thank you, Jim.